Welcome to This Explainer. Today, we're going to unpack something really fascinating, the actual mechanics of how value truly moves on the Bitcoin Cash network. If you've ever found yourself wondering what literally happens under the hood when you hit send on a digital wallet, well, you are in the exact right place. We're going to look at the anatomy of a transaction, the incredibly clever scripts that secure your money, and how this entire open ledger operates totally without central authorities. So let's dive right into this. In legacy finance, a bank keeps a centralized ledger of your account, and they just, update the database numbers when you spend. But how does money actually move on a decentralized network when there are literally no bank accounts? If you assume you have a traditional account balance, you're definitely in for a surprise. To keep things simple, here's our roadmap for deconstructing this engine piece by piece. We'll quickly run through the transaction lifecycle, the UTXO physical cash model, the anatomy of a transaction, hidden fees, digital locks, and finish up with modern transaction types.
Part 1, the transaction lifecycle, from origination to the global ledger.
Okay, let's start with the big picture and follow a single transaction's journey. It is a pretty seamless 5-step process. First up is creation, where you or your wallet build a transaction and choose where the funds go. Second is signing. This is where you use digital signatures to mathematically prove you actually own the funds. Third is broadcasting. And because your signed transaction contains absolutely no secret info, you can broadcast it to any node over Wi-Fi, Bluetooth, a text message, or even just post it on a public forum. Fourth is mining, which is when a miner actually includes your transaction in a new block. And finally, confirmation, making it a permanent part of the global ledger. Moving on to part 2, UTXOs and the physical cash model. So how is this value actually accounted for? Well, here is the crazy part. There are absolutely no accounts in Bitcoin Cash. There's no central account with your name on it. That balance, you see, it's basically an illusion. Your wallet is simply looking at the public ledger, finding all the unspent chunks of value locked to your keys, which we call unspent transaction outputs, or UTXOs, and it's just adding them up to show you a total. To give you a sense of the scale of these outputs, one single Bitcoin Cash divides into exactly 100 million base units, and we call these Satoshis. A single UTXO can hold literally any amount measured in these Satoshis. But there's a catch. Once a UTXO is created, it is completely indivisible. What's really fascinating here is how UTXOs work exactly like physical cash. You have to consume the entire chunk and get change back. Think about it. You can't just rip a $20 bill in pieces to buy a $1 coffee. You hand over the whole 20 and you get $19 back in change. Bitcoin Cash operates the exact same way. If you want to pay 1 BCH, but you only have a 20 BCH UTXO, your wallet consumes that full 20, sends 1 to the recipient, and automatically creates a 19 BCH change output, routing the remainder back to you.
Section 3, Anatomy of a Transaction, focusing on the essential data structure.
Now that we've got UTXOs down, let's look at the actual data fields inside the bundle itself. Every transaction connects together like a chain, consuming previous inputs and generating fresh outputs for the next person. It's essentially just a compact bundle of data with 4 key fields. You've got the version, telling the network which rules to follow, the inputs, acting as pointers to the specific UTXOs you're spending, the outputs, representing the new chunks of value being created, so that's your destination payment and your change, and finally, we have lock time. Lock time is a really cool feature. It's basically like post-dating a paper check, ensuring the network totally rejects it until a specific time or block height is reached. Most transactions just set this to 0, so they're valid immediately. But if you set it below 500 million, it acts as a block height, meaning it won't process until that exact block is mined. Set it at or above 500 million, and it acts as a Unix timestamp, which is simply how computers track standard time.
Part 4, the hidden transaction fees. Let's look at implicit costs and network security.
We absolutely have to talk about how miners get paid, because there's a vital cautionary tale here. There is no designated fee field in a transaction. Let me repeat that, no fee field. So any unallocated input value is implicitly gifted to the miner. Fees are just a mathematical difference between your total inputs and total outputs. If you're manually building a raw transaction and you forget to route your change back to yourself, the miner processing it will happily scoop up that massive difference as their fee.
Let's look at this math in action with Alice's coffee purchase. Inputs minus outputs equals that tiny implicit fee. Alice starts with an input UTXO of roughly 0.0027 BCH. She outputs roughly 0.002 to Bob's Cafe and routes about 0.0006 back to herself as change. That leftover, unallocated value, it's just a few satoshis left on the table for the miner. Thankfully, modern wallets handle all of this math completely seamlessly behind the scenes.
Section 5. Scripts. Programmable digital locks securing value with math. This brings us to the real climax of our explainer: how these outputs are actually secured. Every single output on the network is locked with a small program. To spend it, your transaction input has to provide an unlocking script, which contains your signature that satisfies the conditions of the network's locking script. When a node validates your transaction, it quite literally snaps these two scripts together like puzzle pieces and executes them as one single sequence. And here's how that execution stack works step by step. It transforms this abstract coding concept into a straightforward mathematical puzzle that just has to resolve to true. Bitcoin Cash uses a stack-based language. It pushes data onto a stack, and then operators pop those values off to process them. In this basic example, the script pushes 2, then pushes 3. The add operator pops them off, adds them up, and pushes 5. Then it pushes another 5. Finally, the equal operator pops those 2 5s off, compares them, and because they match perfectly, it pushes true. If that final result is true, the network considers the output legally spent. And because this language has no loops, it prevents infinite loop attacks, which makes the whole network incredibly secure.
And finally, Section 6, modern transaction types, going way beyond simple peer-to-peer payments.
So these scripts open up a whole world of possibilities. Standard payments usually use P2PKH, which just locks funds to an address. But then you have multisig, which allows for escrow by requiring, say, 2 out of 3 signatures to release funds. We also have OP_return, turning the blockchain into a data layer by letting you store up to 220 bytes of metadata, which is provably unspendable, by the way. And P2SH is just a brilliant usability upgrade. It lets businesses hide a massive, complex multi-signature requirement behind a short, normal-looking address hash. That completely shifts the complexity and the fee burden away from the customer making the payment. And the protocol just continues to evolve. Take Schnorr signatures, added back in May 2019. They allow multiple keys to aggregate into one, which dramatically shrinks transaction sizes. Then, in May 2023, the network introduced cash tokens. This means this incredibly secure model can now host fungible tokens and NFTs natively, right alongside BCH. Plus, the network intelligently uses orphan pools. So if a child transaction somehow arrives before its parent because of internet latency, nodes will actually temporarily hold it until the parent shows up, rather than just outright rejecting it. To wrap up our explainer today, I want to leave you with this thought. We've seen how UTXOs perfectly mimic physical cash, how implicit fees organically incentivize miners, and how stack-based scripts mathematically secure every single fraction of a cent without ever needing a bank. So as trustless, programmable money becomes this accessible and this powerful, what traditional financial systems are destined to be disrupted next? How will this reshape the entire future of global finance? The foundation is set. Thank you so much for diving into the mechanics with me today. Keep exploring and definitely stay curious.